Hi, in this video we will learn how to find the derivative of inverse function by knowing the derivative of function itself. So throughout this video we are going to assume that f is a function which is invertible, means that f inverse exists, and differentiable. Well, we know that when you have f and f inverse, there is a good relation between different things of these two functions. For example, if y is equal to f inverse of x, then we know that x is going to be equal to f y. And also if f inverse a is a point on the graph of f inverse, then well, you can right away say that f inverse of a and a, just interchange the components of the points, is a point on the graph of f. And this right away gives me very interesting fact that if I know the graph of f, let's say this is the graph of f, then I can find the graph of f inverse by reflecting the graph of f with respect to or through the line y equal to x. So it will be something like, so at every point you find reflection of that point. So it will go there, this will go there, and this will go here almost, yes. So the graph will be something like, okay, something like that, okay? And every point, let's say at point A, the point on the graph of f inverse is f inverse a, and well, that is reflection of exactly one point on the other side, which will be f inverse a and a. What is important here is that since we are going to deal with the derivative, so the tangent line is going to play an important role. But the tangent line to the graph of f inverse is also, because everything is reflection with respect to line y equal to x, so that is going to be reflection. The tangent line itself is going to also be reflection of the tangent line with respect to line y equal to x. So if y equals to mx plus b is the tangent line to the graph of f inverse at point a and f inverse a, just based on what we did see, what we can get, the tangent line to the graph of f itself at the point you change these two, f inverse a and a. Okay, how do we do this? By interchanging x and y in the equation. So then x equals to my plus b is going to be the tangent line to the graph of f inverse. Well, let me just reorder or change this a little bit to write it as a y equal to something, so I can bring b to the other side, And then if m is non-zero, I can say that y equals to 1 over mx minus b over m. And again, we are assuming that all the tangent lines are, the slope of the tangent line was non-zero. Okay, very nice. Well, what does this give me? So the tangent line, slope of the tangent line to the graph of f inverse is m, and that is the derivative of f inverse at that point. The slope of the tangent line is the derivative. The slope of the tangent line to the graph of f inverse at this point was m, and that is equal to derivative of f inverse at a. The slope of the tangent line to the graph of f at this point is 1 over m. But that we know that is going to be the derivative of the function f at this value. Okay, just by considering the derivatives the slopes of the tangent line, we now see that there is a relation between these two. Inverse 1 over m is equal to that, and m is equal to that. So I can write f inverse prime at a is equal, so see from this right away I can conclude that m is 1 over f prime at f inverse of a. So that means that f inverse prime at a is equal to 1 over f prime at f inverse of a. So we found a relation between the derivatives of inverse function and the derivative of the function itself. This is called the inverse function theorem, which starts like, okay, let f be invertible and differentiable then f inverse is differentiable. Well, and the derivative of f inverse as we computed at any point is 1 over the derivative of f inverse of a. Well, we have to be a little bit careful. This number should not be 0. So the differentiability is okay, where differentiable at x equal to a, where f prime at f inverse of a is non-zero. And so if that is non-zero, then the function f inverse is differentiable and the derivative is given by that formula. So this is the inverse function theorem, and we will use that for different things. So here I need to add 2 remarks. One is that if f prime at f inverse of a is equal to 0, then f inverse is not differentiable at x equal to a. And there's another remark that the way we proved here is very geometric. So if this is remark 1, this is remark 2. The way we proved it is very geometric, but one can prove the above theorem using so-called the chain rule. So this is something that we will learn, and that will be a good practice for us to see how chain rule gives us the same result. Okay. And before we finish, I'd like to do one example that kind of confirms the the inverse function theorem. So we have the function f of x equals to 2x plus 1 over x minus 3. Check that inverse function theorem works for this. Means what? So I have f of x, which is 2x plus 1 over x minus 3. I want to find f inverse of that function. So let me find f inverse. So what is that? Well, remember, we start with y equal to 2x plus 1 over x minus 3. Try to solve it for x, so it will be y x minus 3 equals to 2x plus 1. And then from there you have y x minus 2x is equal to 3y plus 1. And that will give us x, y minus 2 equals to 3y plus 1. And we found the inverse. Okay, we have to change x and y, and the inverse in that case will be f inverse is going to be 3x plus 1 over x minus 2. How about f prime of x? So f prime at x, this is chain rule, yes, 2x plus 1 prime x minus 3 minus the numerator itself times the derivative of the denominator and then denominator squared. Okay, so this will give us 2 times x minus 3 minus 1 times 2x plus 1 over x minus 3 squared. And that will be 2x and negative 2x will cancel each other. And minus 6, yes, minus 7 here. Yes, sorry. X minus 3 squared. Okay. So that is f prime of x. And what about f inverse prime at x? Okay, find the derivative of this guy, which will be 3x plus 1 prime x minus 2 minus 3x plus 1 times x minus 2 prime over x minus 2 squared. And that will give me, do the computation, then simplify, then you will get minus 7 over x minus 2 squared. Okay, now we have f inverse, we have f prime, and we have f inverse prime. So now, the inverse theorem, inverse function theorem, says that f inverse prime at x is equal to 1 over f prime when you evaluate it at f inverse of x. So let's do that. F prime when you evaluate it at f inverse x, this is f prime evaluated at 3x plus 1 over x minus 2. Yes, that is them. And well, what is f prime? It is negative 7 over x. Instead of x, you put this one, 3x plus 1 over x minus 2 minus 3 to the power 2. And what you'll see here is, okay, negative 7. Here we get 3x plus 1 minus 3 times x minus 2 over x minus 2. Okay, you can again simplify that with that. This one, maybe red. This goes away with that negative sign. Here will be plus 6 and 1. So we will have negative 7 over x minus 2 squared. Okay. So let me just simplify a little bit more. That will be negative 7 squared over x minus 2 squared, and that will be minus x minus 2 squared. This one of these cancel is over 7. Okay, now see, f inverse prime at x, we calculated it is equal to negative 7 over x minus 2 squared. On the other hand, we calculated what is f prime of f inverse at x. It is, so it's 1 over that is negative x minus 2 squared over 7. So checking, the inverse function theorem says, are these two equal, as the inverse function theorem says? And you can see that well easily that will work just by some simple multiplication. Minus 7 over x minus 2 squared is the same thing as, really we can multiply that 7 x minus 2 squared. So this is 1 over f prime of f inverse of x, and this guy is f inverse of derivative of f inverse of x. So this is just simple example, but inverse function theorem says that you do not need to compute f inverse. You just need to know what is this guy, and then using the theorem you can find the derivative of the inverse function at that point.